Welcome to the video lecture on double and half angle identities. The identities developed in this section are a direct result of the sum and difference identities that we've already learned. Recall that sine of 2x does not equal 2 sine of x. In other words, you're not allowed to pull that 2 out front. Let's think of one way that you could convince someone that this isn't true. So how could we show that sine of 2x does not equal to 2 sine x? Well, one easy way to do this is to think of a counterexample. So this would mean that you're just trying to find one value of x that if you were to plug it in, you would not get the same thing on both sides. So for example, if we let x equal to some nice angle, say pi over 2, and plug it in on the left side, we would have sine of 2 times pi over 2, which becomes sine of pi, because the 2's cancel. And on our unit circle, sine of pi, that's 180 degrees, and the y-coordinate is just a 0. Now let's go to the right side. So if we plug in pi over 2 on the right side, that would be 2 times sine of pi over 2. Pi over 2 is 90 degrees, and sine of 90 degrees, that has a y-coordinate of 1 on the unit circle. So this is just 1 times that 2 out front. 2 times 1 becomes 2, and obviously 0 does not equal to 2. So that would be one way to show that this is not an identity. It's not true because I can find a value of x that makes it not true. Now the relationships asked for above are stated in the double angle identities. The double angle identities are a direct result of the sum formula. So let's see if we can use the sum formula to figure out how or what the double angle identity is for sine of 2 alpha. So what we're going to want to do is think of changing 2 alpha into a sum. So an easy way to do that is to take 2 alpha and break it down into alpha plus alpha. So we could rewrite sine of 2 alpha as sine of alpha plus alpha, and then we could use our sum identity that we have for sine. So remember how that sum formula works. You take the sine of the first angle, alpha, times the cosine of the second angle, which is also alpha, plus, because we use the same sign in the middle, cosine of the first angle, which is alpha, times sine of the second angle, which is alpha. Now sine of alpha times cosine of alpha is exactly the same thing as cosine of alpha times sine of alpha by that commutative property of equality. So this becomes 2 sine alpha cosine alpha. So this is called the double angle identity for sine. Sine of 2 alpha is 2 sine alpha cosine alpha. So it's not as simple as just pulling out the 2. You also get this cosine of alpha multiplied in there as well. Okay? Now let's see if we can use similar reasoning and a similar strategy to come up with the identity for cosine of 2 alpha. So we're going to change cosine 2 alpha into cosine of alpha plus alpha, and we're going to apply the sum formula for cosine, which is cosine of the first angle times cosine of the second angle minus sine of the first angle sine of the second angle. Cosine times cosine becomes cosine squared alpha. Sine times sine becomes sine squared alpha. So here is one formula for cosine 2 alpha. This is one version of the double angle identity for cosine. But I want to show you that there are some alternative forms here. Remember our Pythagorean identity, which says sine squared of alpha plus cosine squared of alpha is equal to 1. That means sine squared of alpha is 1 minus cosine squared alpha. Or if we had solved this for cosine squared is 1 minus sine squared alpha. So I'm going to use those and substitute into this to get some alternative versions. If we replace cosine squared with 1 minus sine squared alpha and leave this sine squared alpha as is, then that now gives us 2 sine squared alphas. So this becomes 1 minus 2 sine squared alpha. So that's also what cosine of 2 alpha equals to. This is an alternative version of the double angle formula for cosine 2 alpha. Another third option that you sometimes will use is to leave the cosine squared that we got up here alone, but then change this sine squared alpha into 1 minus cosine squared alpha. And if you distribute your negative, you get minus 1 plus cosine squared alpha, and we've got a cosine squared alpha plus a cosine squared alpha, which makes this 2 cosine squared alpha minus 1. So there's actually 3 different versions of the double angle identity for cosine 2 alpha, and you use whichever one is the most useful to you in the problem. Alright, let's try one more derivation here. Let's derive the double angle identity for tangent of 2 alpha. So we're going to use 2 alpha and change it into alpha plus alpha again. And this time we need to use the sum formula for tangent. And the way that one works is tangent of your first angle plus tangent of your second angle all over 1 minus tangent of your first angle times tangent of your second angle. And so this becomes tangent alpha plus tangent alpha on top, or 2 tangent alpha, and on the bottom tangent alpha times tangent alpha becomes 1 minus tangent squared alpha. So here's the double angle identity for tangent of 2 alpha. So here's the list of all the ones that we just derived. Remember, there were those 3 different options for cosine, and then we have our sine and our tangent as well. You will need to have these memorized. It is expected that you memorize the double angle and the half angle formulas. Now these formulas are generalizations of specific formulas. The double angle formulas can be used to rewrite each of the following. So just because you see 2 alpha here on the left and alpha on the right doesn't mean this is the only way these problems can be used. So for example, if I wanted to know what sine of 10x is, we could use this double angle formula to rewrite it. So this would become 2 times sine of, now remember, what's in the parentheses is twice your angle. So what you use on the right-hand side of this formula is always half of what you started with. Okay, if this is 2a on the left, we're only using a on the right, so we want half of the original. So if our original angle here is 10x, then we're actually going to use 5x for both our sines and our cosines. So sine of 10x is the same thing as 2 sine of 5x cosine of 5x. Okay, let's try cosine of 6x. So remember, you're starting with double the angle, and when you apply any of these formulas on the right side, you're going to be using half that original amount. So if we used this first formula, this would become cosine squared 3x minus sine squared 3x, or if we wanted or needed to, we could do 1 minus 2 sine squared 3x, or we could do 2 cosine squared 3x minus 1. All 3 are equivalent. For tangent of 100x, we're going to use our tangent double angle formula. So we want 2 tangent of half of this original angle, which would make it 50x, over 1 minus tangent squared 50x. And then finally, for sine of x over 2, we're going to go back to the double angle formula for sine, which would be 2 sine of half of this angle. So what's half of x over 2? Do top times top over bottom times bottom. This becomes x over 4. So we need 2 sine of x over 4, cosine of x over 4. Okay? Now let's see a couple of common examples that you'll be expected to do using these double angle identities. Suppose that we are told that cosine of x is equal to 2/7. X is in quadrant 4. Find each of the following. And each of these 3 things we're looking for are double angles. So unfortunately, if we want to know what sine of 2x is, that has a different angle. The angle here is 2x. Versus the angle that we're told about, which is just x. So what we're going to need to do here is use our double angle identities and try to break down these initial expressions, these initial problems that were being asked, into angles using just x's. And that's where that double angle formula comes in, because if you start with the 2x and you apply the double angle identity to this, then this would become 2 sine of half this angle, x, cosine of half this angle, x. So now we're replacing that double angle 2x with just x. And now these are values that hopefully we'll be able to figure out given the initial information in the problem. Now we already know what cosine of x is. It's just 2/7. But how am I going to figure out what sine of x is? And the way to figure out that is to go back and draw a triangle. Remember that if you know cosine of x is 2/7, you also know that cosine of x is defined using a right triangle definition as adjacent over hypotenuse. So we can construct a little right triangle here. My angle x in the corner is the reference angle that I'm using, and in reference to that, the adjacent side is going to be, if cosine is 2/7, I'm going to let my adjacent side be the 2, and I'm going to let my hypotenuse be the 7. So what does that force this missing side over here to be? Well, since this is a right triangle, we can use Pythagorean theorem. The hypotenuse squared, which would be 49, minus the adjacent side squared, which would be 4, would give you 45, and we need the square root of all of that. So square root of 45 is square root of 9 times square root of 5, and that reduces to 3 root 5. So our missing side is 3 root 5. Now how does this triangle help us? Well, we know if cosine is adjacent over hypotenuse, then sine is opposite over hypotenuse. Now notice here, it's sine of x, because that's the angle that we're using in our triangle. It's not sine of 2x. I didn't draw a triangle with an acute angle of 2x. I drew the triangle with an angle of x. So everything is in reference to this angle x if we're using this triangle. So the opposite side to angle x would be 3 root 5, and the hypotenuse is still that 7. So we're going to be using for sine 3 root 5 over 7, and for cosine, that's that 2/7. Now there's one more thing that I need to worry about here, and that is quadrants. If we are in quadrant 4, what are the signs, the positives and the negatives, for sine and cosine, since those are the two things I'm using in this identity? Well, in quadrant 4, cosine is positive, because that's an x-coordinate, but the y-coordinate in quadrant 4 is always negative, and the y-coordinate is always your sine value. So this needs to be a negative 3 root 5 over 7, because we are in quadrant 4 for this angle. So now that I know what sine x is and cosine x is, all I have to do to finish off this problem is multiply everything together. So we're just going to do tops multiplied together over bottoms multiplied together. The bottom is just 49, and the top, 2 times 3 is 6, 6 times 2 is 12, and it's negative, and then we have that root 5 next to it as well. So our final answer, negative 12 root 5 all over 49. Okay, now the nice thing about these other two problems is they get to use this same triangle, because our initial information of cosine x equaling 2/7 forces this triangle to be true no matter what problem we're looking at. The only thing that's going to be different for parts B and C is the identity that I use. So if I wanted to know cosine of 2x, remember up here you have 3 choices. You can use any of these 3 formulas that you like. Now since the original information in the problem told us what cosine was, I'm going to go ahead and use this version right here and do 2 cosine squared x minus 1, since we're trying to find cosine of 2x. Now you could also have done the sine squared version, or the one that used both sine and cosine squareds. It doesn't matter. You'll get the same final answer no matter which version of that identity you use. I'm just going to go ahead and use this one here because I know what cosine x is. It's this original 2/7. So if I want to plug in cosine I'm going to plug it in here, but we really want cosine squared, so I need to square that whole fraction. I know that this is a positive 2/7 because, again, we're in quadrant 4, and cosine is positive in quadrant 4. So squaring this gives it, or turns it into 4 over 49, and then if I multiply that by 2, that becomes 8 over 49. I'm not going to be able to subtract this 1 unless I get a common denominator, so if I change 1 into 49/49, 8 minus 49 gives me negative 41 over 49. So that's what cosine of 2x equals. Finally, we want tangent of 2x. So the double angle identity for that, to turn this into something using just trig functions of x and not trig functions of 2x, using that double angle identity, this becomes 2 tangent of x all over 1 minus tangent squared x. So if we're going to use this identity, I need to go back to my triangle over here because this is still valid, but this time I want to know what tangent of x is going to be. So tangent is opposite over adjacent, so that's going to be 3√5 over 2. And we have to worry about our signs again because we're in quadrant 4. So remember, in quadrant 4, the x's are positive and the y's are negative, which is why this sign value was negative 3√5 over 7. What about tangent? Is tangent positive or negative in quadrant 4? Well, it has to be negative because tangents are y's over x's. So this is going to have to be a negative 3√5 over 2. So when I substitute in tangent of x, make sure you substitute in a negative 3√5 all over 2. And then I want 1 minus negative 3√5 over 2. Simplifying on top, the 2's cancel, giving me negative 3√5. Squaring on the bottom, I square the 3 and that turns into a 9, and I square the 5 and that turns into, I square the square root of 5, which turns it into a 5, and I square the 2, which turns it into a 4. And 9 times 5 becomes 45. So this gives me negative 3√5 all over 45/4 being subtracted from 1. I'm going to need that common denominator again, so let's use 4 there. And we're going to get negative 3√5 all over negative 41 over 4. It's getting a little bit messy, but we're dividing by a fraction, which is the same as multiplying that numerator by the reciprocal. So this would flip over to negative 4 over 41. The two negatives are going to cancel out. 3 times 4 is 12, and we get positive 12√5 all over 41. Okay? All right, let's try another one. This time we know that cotangent of x is equal to 2/3, where sine of x is less than 0, and we want to find sine of 2x, cosine of 2x, and tangent of 2x. So again, we're asking about double angles, but the only information they give us is the single angle, reference to this cotangent of just x, not cotangent of 2x. So we're going to have to draw a triangle to help us figure out some of these values, but we also are going to need to convert all of these double angles into trig functions of single x's. So in other words, sine of 2x, we need to change that into 2 sine of just x and cosine of just x, because those values, those sines and cosines, I can figure out once I draw my triangle for this relationship of cotan x equals 2/3. So let's go ahead and draw our triangle. Here's my x down in the corner. Cotangent is the reciprocal of tangent. So if tangent is opposite over adjacent, then cotangent is adjacent over opposite. So I'm going to let my adjacent side be 2, and I'm going to let my opposite side be 3. And using Pythagorean theorem, 2 squared plus 3 squared would be 4 plus 9, or 13, and I need the square root of that for that hypotenuse. So there's my triangle. Now let's worry about our quadrants. Cotangent here was given to us as a positive 2/3. That's important. Which two quadrants have cotangent being positive in? Well, cotangent is positive in quadrant 1, and it's also positive in quadrant 3. We also know that sine of x is supposed to be less than 0. In other words, sine of x is supposed to be negative. So if cotangent is positive in quadrant 1 and quadrant 3, in which of those two quadrants is sine also negative? The only one it could be is quadrant 3. So we have to be in quadrant 3. So whenever we find sines and cosines, we need to remember that these are quadrant 3 values, quadrant 3 angles. So in quadrant 3, sine is negative and cosine is negative. So let's figure out what sine is. According to my triangle, sine is opposite over hypotenuse, so 3 over root 13, but in quadrant 3, that would be negative. And cosine is adjacent over hypotenuse, so 2 over root 13, but in quadrant 3, cosine is also negative. So this double angle identity becomes 2 times negative 3 over root 13 times negative 2 over root 13. When I multiply the tops, my negatives cancel out. 2 times 3 is 6, 6 times 2 is 12, and square root of 13 over square root of 13 just becomes 13. So sine of 2x is equal to 12/13. All right, cosine of 2x, right? Not cosine of x, but cosine of 2x. So to figure out what cosine of 2x is, I'm going to need to use an identity. Again, you have your choices of which ones you wanted to use. This time, just for being a little bit different here, let's go ahead and use the 1 minus 2 sine squared x identity, just for a change of pace. So we know what sine of x is. We already figured that out over here, negative 3 over root 13. So all I have to do is substitute it in. And remember, we're squaring that sine value. So this is going to get squared. So we get 1 minus 2 times 9 over 13, which becomes 1 minus 18 over 13. And if I get a common denominator of 13 and change 1 into 13/13 and subtract, we're going to get negative 5 over 13. So that's the value of cosine of 2x, not cosine of x, but cosine of 2x. All right, finally for tangent of 2x, remember that double angle identity is 2 tangent of x all over 1 minus tangent squared of x. So going back to my triangle over here, I need to know what tangent of x is. You can get it from here, opposite over adjacent, or you could just get it from the fact that if we know cotangent is 2/3, tangent is the reciprocal of that 3/2. And in quadrant 3, if cotangent is positive, so is tangent. So this is a positive 3/2. So we're going to substitute in 3/2 for each of these tangents. On top, the 2's cancel, giving me 3. On the bottom, I get 1 minus 9/4. So this becomes 1 over 4/4 minus 9/4, which is negative 5/4 in the denominator. And that is going to flip into the reciprocal. When I divide by a fraction, that's the same as multiplying by the reciprocal of the denominator. So 3 times negative 4/5 gives me negative 12/5. Okay. Now that's a lot on double angle identities. What we're going to move into now is sort of a derivation of some other identities. So let's go back to that double angle identity we had for cosine. Cosine of 2 alpha is equal to 2 cosine squared alpha minus 1. Remember, this was just one version of that cosine double angle identity. We had 3 different versions. But we're going to use this, and I want to solve this for cosine squared alpha. So here's cosine squared alpha. To solve for it, the first thing I'd want to do is add 1 to both sides. And then I would want to divide everything by 2. So we get cosine squared alpha equals cosine of 2 alpha plus 1 all over 2. And sometimes you see that written as a 1/2 pulled out front, and then in parentheses cosine 2 alpha plus 1. So you could see it written either way. Okay? So we'll come back to that in a moment. Now let's do exactly the same thing for the different alternative version of that double angle identity for cosine 2 alpha. So this is the one using sine squared. So this time let's solve this for sine squared alpha. So if I wanted to do that, the first thing that I could do here is subtract 1 and then divide everything through by negative 2. And to clean it up just a little bit, we can divide that negative into the top. So the positive cosine 2 alpha that I have up there already becomes negative, and the minus 1 becomes positive. And then we could switch the order around on top because addition is commutative. So just to make it look a little bit neater, we could rewrite it as 1 minus cosine 2 alpha all over 2. So here's one version of it. Or if you pull that 1/2 out, it's 1 minus cosine 2 alpha, all of that times 1/2. Okay? All right. Using those two results, let's figure out what tangent squared alpha would be. So if I want to know what tangent squared alpha is, remember that tangent is sine over cosine. So tangent squared must be sine squared over cosine squared. And we know what sine squared is. It's this quantity that we just figured out up here. So 1 minus cosine 2 alpha all over 2. And we know what cosine squared alpha is. It's this fraction right here. So let's put that in our denominator. Cosine 2 alpha plus 1 all over 2. The 2's are going to cancel out. And this becomes 1 minus cosine 2 alpha on top. And just to make it consistent, you don't have to do this, but just to make it consistent, I'm going to switch the order in the bottom and make this 1 plus cosine 2 alpha on the bottom. So there's our formula for what tangent squared alpha is. Now why are we bothering to do this? Well, these formulas that we just generated for what sine squared, cosine squared, and tangent squared are equal to are very useful in calculus in reducing even powers of sines, cosines, and tangents into linear functions of the cosine function. So this is something that you will be doing in calculus if you go that far in mathematics. So for example, you might start off with a function that looks like this: cosine to the 4th x times sine squared x. Now these are pretty high powers for cosines and sines, and it's a product of two of these things. And in calculus, a lot of times you'll be asked to integrate a function like this, and this is just too difficult to do in this particular form. So what we do is reduce these powers, this 4th degree power and this squared power, and we use the identities that we just talked about on the previous page to try and rewrite this as a linear function of cosine. Now linear means to the 1st power. So we're going to reduce these powers all the way down to a 1st degree, and we're going to get a bunch of cosines. So let's see how this might be possible. So one way to do this would be to break down these even powers and try to think about using some of these results that we got up here. And these results were for what cosine squared was equal to or sine squared was equal to. So the very first thing I'm going to do is break down these powers into squares. So all that means is I'm going to take this cosine to the 4th and I'm going to break it down into a cosine squared times a cosine squared, since 2 plus 2 gives me back that 4. So I'm not really doing anything too unique here so far. I'm just breaking down that 4th degree, and then we are going to replace this cosine squared and this cosine squared with this result that we got up here. Okay, so this is going to become, I'm going to use that 1/2 version. So these are the formulas that we're using from the previous page. Cosine of alpha is equal to 1/2 1 plus cosine 2 alpha. That's what we got right here. I just switched the order around. And I'm also going to use this formula for sine squared alpha. So 1/2 1 minus cosine 2 alpha. So the two different formulas look very, very similar. It's just that for sine squared, you have a minus sign. So these are the two results that we came up with before. I'm going to replace this whole quantity for both of these cosine squareds, and I'm going to replace this quantity for this sine squared. And instead of using alphas, we're just using x's. So this would become a 1/2 1 plus cosine 2x. This one becomes a 1/2 1 plus cosine 2x. And sine squared becomes a 1/2 1 minus cosine 2x. So the first thing I'm going to do to start cleaning this up is pull together all these 1/2s. So a 1/2 times a 1/2 times a 1/2 is a 1/8. And then I'm going to have to start multiplying here. I'm trying to get rid of this multiplication. We want to try to write this as a sum or difference of a bunch of sine functions. So you could either multiply these two together first, get an answer, and multiply that by the third one, or what I'm going to suggest doing is multiplying these two together first. And the reason I might suggest those two is because that's a difference of squares. You've got a plus and a minus, so when you FOIL that out, all you're going to be left with is the 1, the middle terms will cancel out, and on the end you'll end up with a cosine squared 2x. So far all I've done is multiply together these last two factors. And that's that associative property. It doesn't matter which two you multiply together first, you'll get the same result. So now I'm going to go ahead and multiply these two together, and I will have to FOIL there in order to do that. So 1 times 1 is 1. 1 times a minus cosine squared 2x stays cosine squared 2x. Cosine 2x times 1 stays cosine 2x. And cosine 2x times cosine squared 2x becomes minus cosine cubed 2x. Okay, so now what we're trying to do, remember, is we're trying to get this down to linear functions of cosine. So we're in good shape because we just have cosines now, no more sines, but we still have powers. We have a square still, and we have a cube as well. So we still need to break down this square and this cube and try to reduce those powers down so that we can get just cosines to the first. So how am I going to do that? Well, this cosine squared, guess what? I'm going to use this formula again. I'm going to use it over and over again until I get rid of all of these powers. So what would cosine squared of an angle become? Well, it's 1/2 1 plus cosine of what? Now here's the tricky part. This formula is for cosine squared alpha, and we double that over here in our formula. So if we're starting with a 2x this time, when I double it in my formula, this is going to become a 4x. Alright, so that one I'm just replacing with this formula again, but this time around I didn't have just an x here, I started with a 2x. This cosine 2x in the middle, I'm not going to do anything with that because that's already to the first power, so that's good to go. But I do have a cosine cubed here, so what I'm going to do is replace this, and I'm going to think of it as a cosine x times a cosine square, a cosine 2x, a cosine 2x times a cosine squared 2x. So I'm breaking down that cube into a cosine 2x times a cosine squared x. And what's cosine squared 2x become? It's exactly what we just figured out over here. It's using this formula again, where that initial angle is a 2x, so it's going to turn into a 4x in our reduction formula. So in other words, this cosine squared 2x becomes 1/2 1 plus cosine of double this angle. So it was 2x, now it turns into a 4x. So each time you apply these two formulas up here, you increase the size of this angle, but you're decreasing the power on your cosine function. All right, we're making progress. We're almost there. We just have to clean all this stuff up. So I have a 1. I'm going to go ahead and distribute my negative a half across. So I have a minus 1/2, a minus 1/2 cosine 4x. We've got a plus cosine 2x. And here I'm going to distribute both the 1/2 and this cosine 2x across. So if I do a 1/2 cosine 2x times 1, it's going to stay a minus 1/2 cosine 2x. Then I'm going to take that 1/2 and that cosine 2x and I'm going to multiply it across to this one. So we're going to have that 1/2 still there, and I can't really multiply a cosine 2x times a cosine 4x and combine it at all because the angles don't match. So we just write them next to each other like that. So this would be a 1/2 a cosine 2x times a cosine 4x. Okay, we're almost done. All we have to do is just combine a couple of like terms here. 1 minus a half is a half. We've got this minus 1/2 cosine 4x. This cosine 2x has a coefficient of 1. This cosine 2x has a coefficient of a minus a half. So 1 minus a half gives me positive a half cosine 2x. And then finally this on the end has a minus 1/2 cosine 2x cosine 4x. Last but not least, every single one of these terms has a 1/2. So let's go ahead and pull it out. And that 1/2 is going to get pulled out and multiplied by this 1/8. So it's going to turn into a 1/16. And we would be left with just a 1 minus cosine 4x plus cosine 2x minus cosine 2x cosine 4x. How do I know I'm done? Because look at all these powers on these cosines. They're all to the first power. That's what it means when it says to write it as a linear function of cosine. Every single one of these is a cosine. I don't have any sines at all. And they're all to the first power. Now granted, their angles are more complicated than what I started with. I started with x's, and now I have 2 x's and 4 x's. But that's the price you pay in order to reduce those 4th degrees and those squares down to a 1st degree. So this is our final answer. We've rewritten the original function as a linear function of cosines, and this is something that you will have to do in calculus. Okay, now remember those formulas that we were just using. So sine squared of x is 1/2 1 minus cosine 2x. Cosine squared is 1/2 1 plus cosine 2x. And tangent squared was just 1 minus cosine 2x over 1 plus cosine 2x. Those are all those formulas that we just kind of derived. What we're going to do now is we're going to turn these into what are called the half angle identities. So what I'm going to do first is I'm going to solve each of these not for sine squared but just for sine of x, or in this case actually sine of alpha. So if I wanted to know what just sine of alpha is, not sine squared, what would I have to do to solve this for just sine of x? Well, I'd have to take a square root of both sides. So if we do that, we're going to end up with a square root, and when you take your square root, you get a plus or a minus symbol out front. And instead of using x's, I'm going to use alpha just because that's the convention in how these formulas are typically written in textbooks. So sine of alpha is now going to be plus or minus square root of 1 minus cosine 2 alpha all over 2. Same idea for cosine. If I want to know what just cosine is, not cosine squared, take a square root of both sides. And you're going to get that plus or that minus symbol, because it could be either the positive or the negative square root. And this is 1 plus cosine of 2 alpha all over 2. And to get just tangent, take a square root of both sides. You get a plus or minus symbol. And we get 1 minus cosine 2 alpha all over 1 plus cosine 2 alpha. Now, to turn these into what we call the half-angle formulas, what we tend to do is change this angle alpha into alpha over 2. Now, how does that affect what happens on this side of the formula? Remember, the angle that you have here is half of this angle. So in other words, the angle that's on the right side is twice what you start with over here. So let's see if I rewrite these in the correct way. If I change this to an alpha over 2, so that if this becomes an alpha over 2 on this side, I need to double that and figure out what that's going to be on the right side. Well, what's alpha over 2 doubled? It's just an alpha. So this is still correct. It's just writing it in a slightly different way, where you tend to see this half angle inside the parentheses, and then you just have your single alpha on this side. And this is typically how it's written in textbooks, but it comes from exactly those same formulas that we were working with earlier, and just changing this argument, this angle inside here, to half its original amount, and therefore changing the angle on the right side to half its original amount. You're still maintaining equality when you do that. So here is what the official half-angle formulas look like. Sine of alpha over 2 is equal to plus or minus square root of 1 minus cosine alpha all over 2. Cosine of alpha over 2 is plus or minus square root of 1 plus cosine alpha over 2. And tangent of alpha over 2 becomes square root of 1 minus cosine alpha over square root of 1 plus cosine alpha. Now that's a pretty messy formula to deal with. If you were to rationalize your denominator and use some identities, it turns out that this result here can turn into either of these two alternatives, and I would recommend using these instead because they're much simpler to work with. And in fact, I tend to like this bottom one the best. Sine of alpha over 1 plus cosine alpha. And I'll show you how we actually use these in several examples. But all three of these are called your half-angle identities. Some instructors require you to memorize these. Some instructors will give these to you on your test. So make sure you check with your instructor about whether or not you have to have these memorized. So let's practice using them. So these are generalizations. We can use them to rewrite all kinds of different formulas and expressions. So suppose I wanted to know what sine of 2x was using one of these half-angle formulas. Let's go back up here and look. If I want to know what sine of 2x is using a half-angle formula, you have to think about your 2x being right here. So what goes inside this formula is always double what you start with, because if this is alpha over 2, we double alpha over 2 to get what's inside this square root. So if I'm starting with a 2x, I have to double it to a 4x and put 4x right here. So in other words, this sine of 2x becomes plus or minus square root 1 minus cosine of 4x all over 2. Remember that sine of 2x is also 2 sine x cosine x. This is the double angle formula. This is the half angle formula. Notice here you've reduced the angle down to x, you've taken half of it, and here when we turned it into our half angle formula we actually doubled the angle. Okay? So it's a little bit confusing there. Let's try it for tangent of 6x. So according to the formula for tangent, if we start with a 6x here, you need to double that, and that's what goes right here and right here. So this would become sine of 12x over 1 plus cosine of 12x. And that's just one version. You could also do 1 minus cosine of 12x all over sine of 12x. Okay, and then the last one down here, cosine of x over 6. So if we put an x over 6 here, remember you need to double that to get what goes inside the parentheses here. So what would x over 6 doubled be? What's 2 times x over 6? Well, 2 goes into 6 3 times, so the doubled angle would be x over 3, and that's what needs to go inside of our square root. And for cosine, it's the plus sign in between. So this becomes plus or minus square root 1 plus cosine of x over 3 all over 2. Okay, let's see some more examples here of how you might use these half-angle identities and so forth. And actually we're going to do a combination of different things here. So we want to find the exact value for sine of 15 degrees. Now if you wanted to know an exact value of a trig function, it better be one of your good angles that you know, your pi over 4s, pi over 3s, pi over 2s, pi over 6s. So those would have to be things like 30 degrees, 45 degrees, 60 degrees, 90 degrees, and so forth. 15 degrees is not one of those good angles. Is there a way to convert it into one of those good angles? Well, if you were to double it and turn it into 30 degrees, that's a good angle. 30 degrees is pi over 6. So if we have an identity which will take this initial angle right here and double it into its double angle, then that would be the one we want to use. So let's write out our two different formulas that we've talked about today. We have our double angle identity for sine, which would say sine of 2x equals 2 sine of x cosine of x. Or we have our half angle identity, which says sine of x over 2 equals plus or minus the square root of 1 minus cosine x all over 2. Now which one of these do we want to use? What we have is the left side. So if this was a 15 right here, on this side of our double angle formula, we're supposed to take half of that amount and use half of that original angle. We don't want to take half of 15 because that would turn it into 7.5, which is something we still don't know. But if we look at our half angle formula and we put our 15 degrees here, we're supposed to double that amount to figure out what goes inside our square root. And if we double 15, then that turns it into that 30 degrees that we want to turn it into. So that's why we want to use the half angle formula on this problem. So sine of 15 degrees, according to this half angle formula, should be a plus or a minus, and we'll talk about that in a moment, square root of 1 minus cosine of double this angle, which turns it into 30 degrees all over 2. Now, how do you know whether you're supposed to do the plus case or the minus case? Just think about what quadrant you're in. 15 degrees is in the first quadrant, and sine is always positive in the first quadrant. So we know what quadrant we're in here, so we're going to use just the plus case. Alright, now all we need to do is simplify this. So think about cosine of 30 degrees. Now it's the same as pi over 6, and for pi over 6 angles, those have a terminal point of root 3 over 2, comma 1/2, and cosine is the x value. So that means cosine of 30 degrees is root 3 over 2. Alright, I want to clean this up. So a couple ways to do that. You could get a common denominator on the numerator and subtract and go from there. I'm just going to go ahead and multiply this fraction on the inside by a fancy version of 1, 2 over 2. And the reason I like to do that is because this then becomes 1 times 2, which is 2, minus, when I do root 3 over 2 times 2, the 2's cancel out, just giving me a root 3. And on the bottom, 2 times 2 turns into a 4. So it's an easy way to clean up this complex fraction. If you want to, square root of 4 is a nice perfect square. So the numerator you're going to have to leave as is, but the denominator you could turn into a 2. So there's our answer, all cleaned up. And you want to leave it with the radicals still in there because it was asking for exact values, which means no decimals. Okay, let's find the exact value for cosine of pi over 8. So remember for cosine, your double angle identity for cosine, this was the one that had 3 different versions. For example, 2 cosine squared x minus 1, and there were other ones as well. Half angle identity for cosine. So cosine of x over 2 is plus or minus square root of 1 plus cosine of x all over 2. So for the double angle, you start with twice what you're going to end up with. For the half angle, you start with half of what you're going to end up with over here on the right. So pi over 8, is that one of our good values? No. But could I turn it into one of our good angles? Sure. Pi over 8 doubled turns into pi over 4. So if we want to figure out which formula to use, which of these formulas take the angle that's here or here and doubles it on this side? Not this one takes half, this one doubles it. So we want to use the half angle formula and make this become cosine of pi over 8 equals plus or minus square root of 1 plus cosine of twice this angle, and twice pi over 8 is that pi over 4 that we were looking for, all over 2. And since we're in quadrant 1, because pi over 8 is a quadrant 1 angle, we just want the plus case. So we've turned this pi over 8 angle into a good angle that we can now use. I know what cosine of pi over 4 is. That's just root 2 over 2. Another complex fraction, because we've got fractions within fractions, so let's just multiply by that denominator, 2 over 2 again. On top, we get 1 times 2 is 2, plus root 2 over 2 times 2 makes the 2's cancel, giving me just root 2. And on the bottom, 2 times 2 is 4. Taking the square root of that denominator turns it into a 2, and the numerator stays root 2 plus root 2. And there's our exact value. Okay, next example here. Find the exact value for 2 sine of 75 degrees. So 75 degrees, that is not necessarily one of our good angles that we know, because if you think about your unit circle, we know 30 degrees, we know 45, and we know 60. 75 is somewhere in there, so that's not one of our good ones. So we need to figure out what we could do to this to turn it into an angle that we do know something about. So the 2 choices to think about are either taking half of 75 or doubling 75, because we have half angle formulas and we have double angle formulas. So which is going to be the better choice? Do I want to take half of 75? Will that turn it into a nice angle? No, because 75 divided by 2 is going to be a decimal. So let's try doubling it. What is 75 degrees times 2? Well, that's 150 degrees. Do I know anything about that? Yes, because 180 degrees is right here, and 30 degrees minus that is right here. So this is 150 degrees. It's equivalent to 5 pi over 6. It's a pi over 6 angle on your unit circle. So that's good. That is something we know. That is a good angle. So what formula, what identity does it take to start with something here and double it on the other side of your formula? So what could we do to kind of figure this out? And look at the format here. This should look a little bit familiar to us based on some of our identities. This looks like 2 sine of an angle times cosine of an angle. And that, hopefully you recognize, is that double angle identity. This product, 2 sine x cosine x, is sine of 2x. So that means that 2 sine of 75 degrees times cosine of 75 degrees is equal to sine of twice this 75, which we said was 150. And that's perfect. That's exactly what we want, because sine of 150, let me write this a little bit neater here, is a good angle that we can figure out. So what is sine of 150? Well, it's a pi over 6 angle, and pi over 6 angles have root 3 over 2 for the x and 1/2 for the y, but 150 degrees is in quadrant 2. So in quadrant 2, the x is negative, the y is positive. So which one of these do we want? We want the sine of it, which is the y value, so we just want 1/2. So sine of 150 degrees is equal to 1/2, which means 2 sine 75 times cosine 75 must equal to 1/2 as well. So recognizing that this problem was initially 2 sine x cosine x, which is the same as sine of 2x, was key. If you can recognize that, then you'll know that you're using that double angle formula. Alright, another triangle problem. This time we are told that cotangent of x is equal to 5. X is between 180 degrees and 270 degrees, and we want to find each of the following. So it's pretty similar to the triangle problems we did earlier today, but the difference is this time what we're looking for here are half angles, not double angles, but half angles. And the information that we're given is in terms of just x, not x over 2. So the triangle that I draw for this relationship, cotangent of x equals 5, is just going to give me information about sine of x, cosine of x, tangent of x, not sine of x over 2, cosine of x over 2, tangent of x over 2. So to figure out what these half angle things are, we're going to need to rewrite these in terms of their identities. So what is sine of x over 2 equivalent to? Well, that half angle identity is square root square root of 1 minus cosine of twice this angle. So twice x over 2 is just an x. That's why we want to do this, because everything that I figure out from here in my triangle is in regards to angle x. So I should be able to figure out what cosine of x is from this triangle. Okay, we'll do that in a minute. Let's write out the other two half angle identities for these other two problems. For cosine, it's plus or minus square root of 1 plus cosine of x over 2. And for tangent, this was the one that had several different choices. My personal preference is to use the one that looks like sine of x over 1 plus cosine of x, because I think that's the easiest one to deal with. So that would be the one I would recommend. Alright, so these are the formulas we're going to need to use, which means we're going to need to know what cosine is from our triangle, and over here we're also going to need to know what sine is from our triangle. So let's draw our triangle. Just draw a generic right triangle. The acute angle in the corner is that x. Cotangent is adjacent over opposite. So if we think of 5 as 5 over 1, then the adjacent side would be the 5, the opposite side would be the 1. And 5 squared is 25, plus 1 squared is 1, so 25 plus 1 is 26, and we need the square root of that to get that hypotenuse. So according to this triangle, cosine of x would be adjacent over hypotenuse, so 5 over square root of 26, and sine of x would be opposite over hypotenuse, so 1 over square root of 26. Now the last thing I need to do before I figure out what's going to happen here is I need to figure out about some signs, some positives and negatives based on which quadrant we are in. And this is a little bit tricky to do with these half angle formulas. So let's think about, first of all, x. What quadrant is angle x in? X is between 180 degrees and 270 degrees. So x is in quadrant 3. So if x is in quadrant 3, what is cosine of x going to be? What sign is cosine in quadrant 3? it's a negative. So this needs to be a minus 5 over root 26. And in quadrant 3, sine of x is also negative. So this needs to be negative as well. Now there's another issue here as well, and that's these plus or minus signs that I have out front of my square roots. Those are a little bit tricky. So here's how you can figure that out. If we know that x itself is between 180 and 270 degrees, then what would x over 2 be between? Well, it would be half of 180, which is 90 degrees, and half of 270, which is 135 degrees. What quadrant is x over 2 in? Well, 90 and 135, that's putting us in quadrant 2. So the original angle x is in quadrant 3. The angle x over 2 is in quadrant 2. So what is that important for? Well, think about what sine of x over 2 would have to be. Is it positive or is it negative? Well, in quadrant 2, sine of x over 2 is supposed to be sine of something in quadrant 2. So in quadrant 2, sine is positive. The y value is positive. So we want to use the plus square root because sine of x over 2 is going to be in quadrant 2 and sine is positive there. Okay, so that's a little bit tricky. We're using positive and negatives in different ways. We're using just the x itself, and that's how we got these negatives here. And then we're using the x over 2 and thinking about what quadrant it is in to determine whether we're using positive or negative square roots. Well, how about this one over here? What's the sign of cosine if we're looking at angle x over 2? So this is quadrant 2, and cosine should be negative in quadrant 2. So that's why out of these two choices, plus and minus, you need to use the negative for this square root, but we use the positive for this square root because in quadrant 2, which is the quadrant that the angle x over 2 is in, we're using those signs, positive for y, negative for x. Okay? All right, we got all the building blocks in place. Now all we have to do is plug in our values and simplify. So let's go over here. We're going to use the positive square root, and then we know what cosine x is. That was negative 5 over square root of 26. So we just need to simplify this. First thing I'm going to do is make this double negative become a positive. Then I'm going to multiply by root 26 over root 26. I'm going to get rid of that common denominator. I'm going to use that common denominator to get rid of this complex fraction. So we're still using the positive square root. 1 times root 26 is root 26 plus 5 over root 26 times root 26 makes these cancel out to a 5. And in the denominator we have 2 times square root of 26. Now this is very messy. It's got lots of radicals within radicals, but that's as far as you need to go for me. Just get rid of your complex fraction and then you can call it quits. Okay? So there's our answer for part A. For part B, this time we want to use the negative square root because we're dealing with a cosine, which is negative in quadrant 2. And we're going to substitute in cosine of x, which was that minus 5 over square root of 26. So pulling the same trick again, let's multiply by root 26 over root 26. We're going to have a negative out front. 1 times root 26 is root 26, minus, because of the negative, these cancel out, giving me that 5, and in the denominator, 2 root 26 stays put. So there's part B. And finally, for part C, sine of x was negative 1 over square root of 26, and cosine was negative 5 over square root of 26. So if I multiply by root 26 over root 26, these will cancel out, giving me a negative 1 on top. 1 times that gives me square root of 26, and negative 5 over root 26, these cancel out, giving me just a minus 5. I personally Don't care if you have a radical in your denominator. Some instructors may require you to rationalize your denominator, which would require you multiplying by the conjugate. But I'm just going to leave my answer like this. Okay, moving on, we're going to talk next here about a few proofs for verifying some identities. So this time we want to show that 2 tangent x over 1 plus tangent squared x is the same as sine of 2x. So if you're asked to prove this identity, remember what you want to do. You're trying to start with either the left side and turn it into the right side, or start with the right side and turn it into the left side. Now, which side here has more to go on, has more to work with? I personally would say this fraction side, because I can change some tangents into sines and cosines, and hopefully that will give me a place to start and try some stuff. So let's go ahead and work with that left side. So since I have a sine on the right side and no tangents, let's change these tangents to sine x over cosine x. And I'm going to do that in the bottom as well. Sine x over cosine x, and we need that squared. So what I'm going to do next here is go ahead and try to, let's square out that bottom and clean up the top here a little bit. So 2 sine x over cosine x all over 1 plus sine squared x over cosine squared x. And this is a complex fraction, fractions within fractions. So if I look at this denominator and this denominator, the bigger power is the one I want to use for my common denominator. So I'm going to multiply by cosine squared x over cosine squared x. And let's see what that gives me. On top, one of the cosines cancels, leaving me with 2 sine x and a cosine x. On the bottom, I have to do 1 times cosine squared x, and then on this fraction, cosine squared x times cosine squared x leaves me just that numerator, sine squared x. Okay, I hope you see this. Cosine squared x plus sine squared x, what is that? That's 1. That's that Pythagorean identity. So this just becomes 2 sine x cosine x all over 1. And what does 2 sine x cosine x become? That's that double angle identity that we've learned today, and that is just sine of 2x, which is exactly what we were trying to prove, so we got it. Okay, so today we've learned double angle identities, which you absolutely need to memorize, half angle identities, which some instructors will require you to memorize, and I probably would recommend that you memorize them because they are pretty handy and you will definitely need them in calculus. But some instructors will give those to you. It just depends. We're going to finish off today with a few more identities, but these you definitely do not need to memorize. They're kind of complicated to remember all the cases. So these I would give to you on a test if you were required to use them. They're known as the product to sum formulas and the sum to product formulas. And they're also listed in your textbook, usually on the back flap of your book. So you don't need to have these memorized, but you do need to know how to utilize them in different problems. So these first 4 are called sum to product because you're taking a sum of 2 trig functions and turning it into a product of 2 trig functions. So here we took the sum of 2 different sines and we turned it into the product of a sine and a cosine. So there's 4 different cases: sine plus sine, sine minus sine, cosine plus cosine, cosine minus cosine. And then down here we have what are called the product to sum. So this is if you have 2 functions already multiplied together and you turn them into either a difference or a sum. So we're going to use those to help us on a couple of problems. So let's look at this next one down here. We want to prove this identity. So we're going to start with either the left side or the right side and trying to turn it into the opposing side. So if we look at this, to me again, there looks like there's more potential on this left-hand side. But we don't have any identities that we've talked about so far, or we've used so far today, that deal with sine of 3x and sine of 7x. So what you want to notice is that this looks like the sum of two signs, kind of like this identity right here, and the denominator is the difference of two cosines, just like this one down here. So I'm going to think of this as my x, and this as my y, this as my x, and this as my y. So let me rewrite our identities that we're going to use so I can push the page down here a little bit. So the way this sign one works is you turn it into a product by adding the x and the y and dividing by 2 and subtracting the x and the y and dividing by 2. And then you do something similar for cosines. Alright, so here are the two identities that we're going to be using. Let's go ahead and try them out. So if I have sine of 3x plus sine of 7x, what that's going to turn into on this side would be 2 sine of this whole thing plus this whole thing. So 3x plus 7x all over 2 times cosine of this whole angle 3x plus this whole angle 7x all over 2. Oops, sorry, there should be a minus sign in between there from right here. Okay, so for the sine you add, for the cosine you subtract. So the top turns into this, and we'll simplify it in just a moment. On the bottom, when you have a cosine minus a cosine, then that turns into negative 2 sine of the sum of the two angles, so 3x plus 7x all over 2, times another sine of the difference, so 3x minus 7x all over 2. So that's how we apply these sum to product formulas. Now we just need to simplify here. So if we add, we're going to get 3x plus 7x is 10x over 2. And if we subtract, 3x minus 7x is negative 4x all over 2. And we get that in the bottom as well. Oops. And what we're looking for here is what we can reduce. So if you wanted to, you could cross off a couple of 2's here. And you can also reduce this 10x over 2 to a 5x, or you could just notice that you have the sign of that on top and bottom, so those are going to cancel no matter what. We have this negative floating out front, so I'm just going to pull that out front. And let's go ahead and reduce this to a negative 2x. And on the bottom, let's reduce it to a negative 2x as well. And then think about cosine and sine in terms of even and odd functions. So what is this going to turn into? Since cosine is an even function, any negative that you have next to that angle is going to disappear. It's not necessary. So in other words, cosine of negative 2x is the same as cosine of positive 2x. However, sine is odd. So if there's a negative in front of that angle, that negative can get pulled out. And this becomes minus sine of positive 2x. So this minus and this minus will cancel out. And cosine of an angle over sine of that same angle, that's a cotangent function. Cotangent is cosine over sine. And what's the angle that they both share in common? 2x. So we got this to be exactly what we were trying to get. Okay, next one here. Write as a sum. So we have sine x, sine of 5x. That's a product right now. It's a sine times a sine. We want to turn it into a sum. So let's look at our choices up here. We have a sine times a sine, so it's this formula that we want to apply. So let me recopy it so that we have it a little bit more visible. So sine of u sine of v is equal to 1/2 cosine of u minus v minus cosine of u plus v. So that's the product to sum identity that we're going to use. So sine of x times sine of 5x should become 1/2 bracket cosine of, this is our u, this is our v. And we want to subtract those right here. So x minus 5x. Then we subtract from that cosine of u plus v, so x plus 5x. And now let's simplify. X minus 5x becomes negative 4x. X plus 5x becomes 6x. And remember that cosine is an even function, so this negative can disappear. So to simplify it, it would be 1/2 cosine of 4x minus cosine of 6x. And there's our sum. It's actually a difference, but it's a sum of a negative. So here's our answer. Okay? Now we're going to go the other way. So this time we want to write it as a product. So this is a sum, and we want to turn it into a product. So let's see which formula applies. We've got a cosine plus a cosine. So out of my list up here, I want a cosine plus a cosine. So I want this formula right here, which is 2 cosine the sum over 2 times cosine of the difference over 2. So cosine of x plus cosine of y is 2 cosine of the sum over 2 times cosine of the difference over 2. So this is going to become 2 cosine of the sum of these two angles, so 5x plus 2x all over 2, times cosine of the difference of those two angles. Reducing, 5x plus 2x gives me 7x over 2. 5x minus 2x gives me 3x over 2. And there's my final answer. Okay, our last example. Suppose that we have a rectangle inscribed in a semicircle of radius 1. Let's draw what this illustration should look like. So here's my semicircle. Radius 1, you could even put it on some axes if you want. So this is 1, this would be negative 1. And we have a rectangle inside of it. That's what it means to be inscribed inside. Express the area of the rectangle as a function of the angle theta shown in the illustration. And the angle theta that we're talking about here would be this angle right here to that corner where it's hitting the circle. So let's think about how we could find out the area of this rectangle just in terms of this angle theta. So to do this, the first thing you might consider doing is just thinking about how you would normally find the area of a rectangle. Normally when we think about rectangles, we just do length times width. So let's figure out some dimensions for our rectangle here. I'm going to, if I center this along my coordinate system and think of this as the origin, just to make my life a little bit easier, let's call this x and let's call this height y. So in other words, this ordered pair right here is x comma y. So the length would actually have to be another x over here as well, just going in the opposite direction. So my full length is actually 2x. And my width here is the y. So my area, length times width, should be 2x's times y, or 2xy. Now, that's an area formula, but it's not in terms of theta. It's in terms of these x's and y's. So how can we convert this into something in terms of x's and y's? Well, the way that we're going to do that is we're going to realize that we're on a unit circle here. We're on a circle of radius 1. So this corner point right here, which I'm calling x comma y, has what other equivalent coordinates? Well, on a unit circle, the x coordinate is also known as cosine of your angle, and your y coordinate is the sine of your angle. And that's what this theta is, because this is that angle that's starting on the positive x-axis and going towards that terminal point. So this is that theta right here. So in other words, x is just cosine theta and y is just sine theta because we are on a unit circle. So what I could do then is I could take this area formula, x times y, 2x times y, and turn it into 2 times x, which we're calling cosine of theta, and y, which we know is sine of theta. Now, how do I show that that becomes sine of 2 theta? Well, if we just rearrange the sine and the cosine, then this is exactly that double angle identity. So we know that that is the same as sine of 2 theta. So another way to write this area, not in terms of x's and y's, but in terms of theta, would just be sine of 2 theta. Okay, now that we know this area function in terms of theta, what angle theta would it take to make this area be as large as possible? So if my area function is sine of 2 theta, when does area get its largest for what choice of theta? So let's think about this function here, sine of 2 theta. When is sine the largest? At what kind of an angle? So in other words, what would this have to be right here so that sine of it would be as large as possible? When does sine become its largest? Well, on your unit circle, the largest value that sine can take on is 1, and that happens right up here at 90 degrees, or pi over 2 radians. So if we want this to be pi over 2, because we want sine of pi over 2, then we need 2 theta to be pi over 2. And that way sine of pi over 2 would give us 1. So this area is going to be its largest with a value of 1 when theta is what? Well, let's solve over here. When does 2 theta equal to pi over 2? Well, I could just divide both sides by 2, or in other words, multiply both sides by a half, and pi over 2 times a half is pi over 4. So when theta is pi over 4, the area is largest, and the actual area will be 1. Okay, so we need our angle theta to be pi over 4. So when it's pi over 4 right here, that will give you the rectangle that has the largest area. And you can kind of visualize why that would be true. Okay, 45-degree angle right there. So what would be the dimensions of this rectangle? So what would be its x and its y? Well, remember, x is cosine of theta, and y is sine of theta. So if the theta that is best is pi over 4, then what would cosine and sine of pi over 4 give us? Well, it would give us root 2 over 2 for both of these. So we would need x to be root 2 over 2, and we would need y to be root 2 over 2. And there's our x's and our y's. Okay? All right, a lot of identities today. Please memorize the double angle identities, and I would strongly recommend that you also memorize the half angle identities. You do not need to have memorized the sum to product and product to sum identities, but you should know how to use them in problems. All right, good luck. That concludes our lecture on double and half angle formulas.